Every time we generate a sample, the values of the random variables change. However, some patterns remain the same. For instance, when we sample from a Gaussian, we generate more values at the center of the distribution than at the tails. How can these regularities be quantified? One way of characterizing them is by defining expected values. So let's say that we have x, which is a random sample from a PDF, f sub x. And let's take a function, a real-valued function, g, that is a function of x. Since x is a random variable, g of x will also be a random variable. We'll define the expected value, the expectation of g of x under that PDF as the integral of this product, the PDF times g of x. A common way of characterizing a random variable is by specifying its moment. Moments are expected values of powers of the random variable or of the random variable with the mean subtracted. Let's see a few of these moments. The mean is just the expected value of x, the random variable. The variance is the expected value of the variable with the mean subtracted squared. From the variance, we can define the standard deviation. Standard deviation is just the square root of the variance. This gives us an idea of the scale at which the random variable is changing. Finally, we can define the central moment. The central moment of order k will be defined as the expected value of the random variable with the mean subtracted to the power k. For instance, the variance is simply the second order central moment. From the central moment, we can define different quantities that characterize the shape of the distribution. For instance, the skewness, which gives us the asymmetry of the distribution, is just defined in terms of the third order central moment normalized by the variance to the 3/2. The skewness of a Gaussian distribution and of any symmetric distribution is 0. The kurtosis is used to measure the heaviness of the tails. It is simply the fourth central moment normalized by the variance square. The kurtosis for the Gaussian distribution is equal to 3. Distributions that have a larger kurtosis than the Gaussian are going to be called leptokurtic. So leptokurtic, heavy tails. Distributions that have thinner tails than the Gaussian will be called platokurtic. In finance, we often find distributions with heavy tails, therefore they will be leptokurtic.